It's a pleasure to introduce Alex Shapiro, who's well known to all of you. I mean, he's a Russell Chandler III Chair and Professor in Industrial and Systems Engineering at Georgia Tech. Too many awards to list, but recently he had a Danzig Prize for Mathematics, Mathematical Optimization Society in Siam, and this year was elected to the National Academy of Engineering. My pleasure to introduce Alex, and I don't have the title in front of me, so I'll let you state it for us.
Thank you very much. How much time do I have? When I should
yeah, you've got 30 minutes, yeah.
30 minutes, yes.
Yeah, leave a couple minutes of questions if you can, but.
After such introduction, I'm intimidated.
Mm-hmm.
Let me open this. Let me do this share screen, right? Share screen. It's Control L. No, doesn't work. Can you see my screen?
Yes, it looks good.
Oh, okay, it's good. Okay, so I can start, yeah? Okay, so let me say first a few just general words. I listened to many talks here, and what I will talk about probably different point of view of that, of the stochastic optimization. It's going backwards, long way backwards, probably origins of linear programming with Danzig and all that. And in my opinion, this recent years, it was a very considerable progress in that. And I would say even different point of view mainly from computational point of view, what can be solved, what cannot be solved, and how to do that. So let me first state a general setting, which is reasonably simple, right? Suppose we have a random process. You can think about that as the sequence of random vectors. This is your data, and this is just notation for this, for the history of the process, and then we make decisions. All right? In that sense, it's very similar to what everybody talking about that. But next is this formulation, what I say, and it's somewhat different here. All right? So again, we have objective functions, and we suppose we have certain period of time over the horizon, and we want to say minimize. It's on average. We minimize the expected value. This is so what is important here, and it's probably different from what I heard so far. The first simplifying assumption, is that the process, that the distribution of the process, it's supposed to be a random process, but its distribution is not influenced by our decision. This is very important assumption. Why it's like that, I will explain in a moment. Yes? So in other words, the distribution of this data process doesn't depend on our decisions. And I will mainly talk about linear case. So this what is here is basically typically balanced equations. There are also local constraints. In this formulation, there's no clear separation between state and state variables and control variables. It's not that important anymore, right? So if we take this point of view, so our policy is just a function of the information that we have at the time t. Now, the question is, can this be numerically solved? At this point, and this is what I will talk about. This is where all the progress is. Now, from this, what is written here is, if we take at this point of view, we have to solve this infinite dimensional problem, because typically, from modeling point of view, the sequence of random vectors there, it can be even more complex than that, are continuous. Now, because of that, our decisions at every point of time is a function of the history. And if we take point of view of continuous distributions, it's infinite dimensional problem. So in order to somehow to solve that, even to put it in a computer, I need to discretize that. And the huge progress that was in recent years and all this by using randomization methods. Okay. Now, traditionally, if we're going back to stochastic programming, this was all formulated in terms of scenarios. So if you look all these old books on stochastic programming, you see this construction of scenarios 3. This is what is assumed to be happen in the future. So if I go back to that, right, can it be really solved, this problem? What it means even to solve this problem, right? The complexity of that is growing fast, both with respect to dimensions. You say the state, usually one need to keep track of state variables. I'll talk about that. With dimension of that, of decision variables, and with the number of stages. And today we have reasonably good understanding of complexity of that, say sample complexity when randomize that. And the conclusion of that is very pessimistic. And from optimization, from even a historical point of view, it's all started with 2 stages, right? Even 2-stage, solving 2-stage exactly is probably out of question, because one has to compute the expectation value, which is integral, and its dimension of random growth, one cannot compute it accurately. So the huge progress was made by some randomization methods. I will not talk about that. But even linear case, when we have this constraint, and you see this typically balanced type of constraints, this Markovian type of constraints, because we only look at one period before that. And even if our functions are linear, it's linear problem, it seems that generically it's computationally intractable. There are very strong results about that, saying that, and it's understandable why. So, nevertheless, one cannot dismiss it that easily. So, what can be solved? And why I'm talking about that? Because if the functions here are convex with respect to decision variables, and we have this linear constraints, it's a convex function. So basically, if we have finite number of scenarios, scenarios are possible realizations of our process. Right? If it is all linear, it's possible, and these constraints here, usually it's simple type of box type of constraints. One can formulate it as one large linear programming problem. It's called a deterministic equivalent of that. But the number of variables in that grows exponentially, both with dimension of this random variables, random vectors, and number of stages. And very quickly it becomes astronomically large, practically impossible to do anything about that, right? So the other point here that probably I should say now a few words, because it's, I suppose. Now, how we know the distribution of that? Even formulation here, no, there are many questions about that. Why we compute it on average, take an expected value, even if mathematically I want to formulate it, I need to know the distribution of my random process. So another program, another direction, and it became very popular now. So we don't know really the distribution of that. So we take certain family of distribution and we look at min-max problem. So in a static case when we have the objective function, say 2-stage, when we, from computational point of view, that for a given x and realization of random data, I can compute the value and probably say subgradient or something like that. Convexity in optimization, classical optimization, is very, very basic. It's more important than differentiability, right? So in a static case, classical formulation is, okay, I will take the worst possible case with respect to certain family of distribution. How to choose this family? There's a long, long discussion. I don't have time about that. Now, how we can even formulate that in multi-stage case is not obvious at all. When we have this static case, when we have just objective function, there is no dynamics here. Right? No, it's reasonably clear. Of course, we take the expectation with respect to consider this distribution, no, and we take maximum of that. If everything is okay, it's reasonably clear what is there. Now, when we go to a multi-stage setting, it's not clear at all what it means. And there are quite non-trivial technical questions about that. I don't have time to talk about that. One of the possible approaches about that is to assume that there's a reference measure and the set of distributions that we consider, and I'll talk immediately, we'll talk about dynamics now, is absolutely continuous with respect to certain reference measure. Usually it's coming from the modeling. And then they say, okay, our modeling is not exact, so there's a certain set of distributions, we can model that somehow. And the moment I'm talking about that, I can consider the corresponding functional of that, which is defined by the worst possible case. If I'm going back to that, I can look at that, I can think about that as a functional of that. And this functional has all types of properties. So from this point of view, it's very natural to talk about low invariance of that. In other words, it's only depend on the distribution of our data of that with respect to the reference measure. And in all these constructions, it's important. Okay. Again, if we, because we talk about the sampling here, right? If I assume that it's low invariant, it's only depend on the distribution of that, I can probably construct the sampling approach of that. I assume that I can sample from the reference distribution, or in other words, when I observe a random data, it's coming from the true distribution. Right? I can probably resample that, or I can build a model of that, and I can sample it again from that. And then when I look at its functional, I can talk about discretization of that by randomization. And then there's a lot of theory about that. Okay. No, it's there's possible to show this low invariance. You can look at the low invariance from the point of view of the functional, which is very natural, or from the point of view of the set of densities that correspond to the chosen set. And it tends to be this equivalence between these two. You can go from one to another. Now, and this is just okay. Now, one of the classical examples that I can talk is the so-called, it has many names. It's called average value at risk, conditional value at risk. It has also long story, very long history. It was used in economics maybe about 100 years ago in different form. It's one of the examples of the very natural examples of risk functional that one can construct. Somehow this gives penalization on our high levels of that. If it go considerably above the average, give penalization. So it's very natural to talk about this type of risk measures. And again, there's a long history about that. This is example of this so-called lower invariant coherent risk measure. Again, there's a long, long history about it. Now, let me talk about dynamics. I don't have much time. So one immediate question that we have, how to extend this type of robust distribution, it became recently known under the name robust distribution, to multi-stage setting, to dynamics. So it looks very natural, right? One has this objective function. No, there are constraints, feasibility constraints. We optimize it over policies, right? Which use a certain set of distributions of our random process, and we take this type of min-max. It turns out that this is not correct formulation. Why it's not correct formulation? For several reasons. It doesn't take this formulation, if we take it looks natural, doesn't take into account the dynamics of our process. And the original dynamics is conditional. Every time we make the decision, it's a conditional what we observed so far. And this, when we take expected value, it has very natural property of this. It has various names that conditional, if I take conditional expectation and expectation of that, it becomes expectation. Average of averages is total average. When we go to more complex cases like that, when we have distributionally robust or risk averse, it doesn't happen anymore. So it's very natural because of that, because of I'll start to write now dynamical equations. This is how one can solve this type of problem. One needs to consider this certain type of nested formulations of that. I try to write it nested formulation. So if this is singleton, right, I'll have simply, in other words, I'll consider only one probability distribution. It will be usual because of this tau property of expectation, will be usual expectation. But when I consider the maximum of that, I need to take, and I take maximum with respect to that inside this nested formulation, which I need to formulate for dynamics of that, it's not the same anymore. I only even wrote it what is called essential supremum, because it's not clear what is really supremum of that. One cannot take pointwise supremum because it has many problems, measurability and some other problems. So this is not a trivial. I don't have time to go here. This really not trivial technical details about that. But what is interesting? No, if you, for example, if it is finite, all of that, this is a reasonably simple thing. Or say, if you have this discrete distribution, then one can take pointwise maximum of that. What is interesting of that? There is one measure, risk measure, one set of measures, such that I can write this functional net form. But it's very complicated. It's coming from the nested form. And it will be not the same as this one. Even in the simple case that I will say now, when we will have this so-called, this rectangular property of that, even then it's not the same. So when if I do it like that, this nested formulation, I can write it one form. In the previous case, it was just expected value, but here it's something else, which is not observed directly. Okay? But what we can do, we can write dynamical equations. And the dynamical equation will look like that. So if I make no assumptions about the process, I have to keep track of all history of the process. It's useless because of that. I cannot use it for computations because then I have to keep the track of all history. It will be impossible. So one huge simplification of that, if I assume that my set of probability measures has a rectangular structure, it has different names, but it looks very natural. So I can see this, my set of my probabilities has this some type direct product structure. So if it is, if this is a singleton, if it is just one, it means that this marginal distribution of my data process is stochastically independent of each other. Right? So here I need to only to model marginal distributions of each random vector. I don't have to keep them together. This is huge simplification. And of course, the question is that how it's in a practical application. Is it okay or not? No, it's a long talk. I don't have time to talk about that. Sometimes, usually it's Markovian structure. Sometimes one can reduce to that. But I don't have time to talk about it. So in rectangular case, my dynamical equation simplify enormously, right? So in other words, here I have to deal with only with the marginal distribution of my each random vector. And it's a value function. If I go to the value function, if I take the corresponding expected value function, only depend on state variables. No, I didn't say what state variable so far, but in application, it's usually like this. It's still enormous simplification of that. Now, yet, there are two basic questions if I want to solve that numerically. And this is all about, at the end of the day, if it to be useful, I somehow had to solve that. One question is, if this has continuous distribution, I had to discretize that. And we have quite good idea of today what it means. No, because I have to deal only with the marginal distributions, I can sample from the marginal distribution. No, for suppose I have t stages, and I sample from each one of them, say 100. I have random vector, and by using Monte technique, from each one I sample 100. The total number of scenarios, even by that, if I do it like that, grow exponentially because I have to multiply that. So if I have even have say 3-4 stages, it's already become astronomically large, impossible to deal with that. But nevertheless, I can look at these value functions or cost to go functions. The next questions, if I discretize them, right, I have to only deal with the state variables. How can I deal with that? One way, of course, I can also discretize my state space. This is out of questions if dimension of that is, say, 3 or even 3. And here we deal with sometimes of dimension 10, 20, 100. Nobody solves course of dimensionality problem, but sometimes, in some cases, something can be solved. This is the point. So the main point here that the value functions are convex, if I, for example, consider linear case. And this is extremely important. So this natural idea now is try to approximate this value function by cutting planes. This is going a long way back to in discrete deterministic case to so-called Kelly algorithms at 60 years ago, right? And it's after that was huge progress on that. In deterministic case, probably this cutting plane type methods based is level method of Nesterov-Nemirovsky. But anyway, the idea is the following of that, and it became quite successful for solving some classes of problems, right? So the idea is to approximate the value function by cutting plane, going backward and forward. In other words, this we start from this last period of time, and then we generate certain what is called trial points when we add additional cut to our value function, and we know how to do that. So at every iteration, we have lower approximation of our value function by piecewise affine functions, which give us support for them. And we're going backward, adding more and more cuts. In this classical list type of algorithm, in the forward, after I generate certain approximation of the value function, I can go forward, generate a random sample of that, and that gives me point estimate of the value of the current, this approximation of policy, and also when I will make the next approximation. This has become known as the DP algorithm, and it can be extended to risk-averse case quite naturally, and sometimes it works. How much time I have?
7 minutes.
7 minutes, okay. No, I still have some time. So if we look, if we look at that, this say expected value, what is called risk neutral, right? We optimize it on average. After we generate random sample we sample from each marginal distribution, we have the value, current value. It's possible to show that on average it gives us low bound for the true value of that. So because of that, we can construct lower bound and upper bound for the true value of our problem and see how it converges to each other. Okay. Maybe this this important point here. The moment I construct this approximation, I generate a feasible policy for my problem, assuming this that has what is called relatively complete recourse. Infeasibility doesn't happen. Because I can go forward, generate a random sample path, it's called scenario, right? And every time I go forward, I solve the corresponding equation, this linear programming, and it generates one possible solution for this generate sample path of my problem. Okay? So it can be done I can do it for original problem, what is called true problem, with continuous distributions by randomly sampling from continuous distribution, or I can do it for generated discretization, both. And that gives me an idea how well I solve the problem. It gives a lot, because of that, I have an upper bound, which is statistical. I simply have I generate many sample paths. Right? For each one of that, I get point estimate and I average that. It works sometimes reasonably well. And I have the lower bound. Okay. This is what it's trying to say. Now, as I said, this the complexity, computational complexity of that grows fast, with generally with the number of stages and the number of this dimension of the state variables, how many state variables I have. Why this method sometimes works at all? We don't have very clear understanding of that. Empirical the experiments that we have sometimes work reasonably well. Sometimes we solve the problem with very large number of stages, 120 stages, something like that, with reasonable variability of the data, right? With the state variables, say 10, 20, something like that. It seems to be the reason that from complexity point of view, one cannot really approximate high-dimensional function, even convex, uniformly everywhere. No number of cutting planes start to go exponentially if you want to approximate it uniformly. But we probably, when we deal with real applications, we probably don't need to approximate the value functions everywhere. Sometimes it's low dimension. Probably this all go around much lower dimension that dimension of the state variable. Sometimes probably in several places. We don't have clear understanding of that. This is one of the big questions of that. Another problem is that why we need so many stages, which some in application people try to do. I saw a talk where the people talk about 10,000 stages. What you can do with 10,000 stages? Moreover, how you can predict your future that far? In application, it's almost always people use a first stage solution, or maybe second for some reasons, and then it's recalculated as the new information is coming in. So the question, one of the big questions, how far in the future I should look to have a reasonable first stage solution? In many cases, at least what I know, the problem has periodical behavior. No, there's some problem that we solve it on monthly basis, something. It's a year has 12 months, and that basically in forecasting, it's repeat itself more or less, because otherwise how one can predict final future. So it turns out that one has this certain periodical behavior of that. It's possible to drastically reduce number of stages by using this periodical behavior. And the ideas here are similar to ideas what people use, of course, in optimal control and MDP. But there's an essential difference here. All right. First of all, we still, even if we have, say, period 12, on monthly basis how to solve them. After this, and what I wrote is somewhat standard, right? We have discount factor, and we have certain type of period, and if it repeats itself, we can write the corresponding, no, this we need to make certain assumption, the corresponding type of dynamical equations. It's possible to do in risk averse and risk neutral case, and sometimes it allows to drastically reduce the number of the stages, keeping the essential things of the problem. One of the reasons why the people use the many stages is end of horizon effect. Because if one uses very few stages, the algorithm will at the end say, use all your resources, because it doesn't care what happens afterwards. Right? Because of the deal with that, people use many more stages of the effect. This take care automatically. I suppose I have to finish in a moment, right?
Yes. Yeah.
Okay. So it's possible to do that. I don't have time to talk about this. This is an example of this, how we solve huge problems sometimes using a low and upper bound. Upper bound is computed by a certain dual, solving certain dual problem. And one of the big problems in all that, when discount factor get very close to 1. It's well known, in that case, it's become more and more difficult. So even and the duplications that we deal with, the discount factor is very close to 1. It's 0.99, something like that. And yet it was possible to solve with reasonable accuracy. Okay, questions?
Oh, great. Thank you very much. I think that we're going to have a break right after the next speaker. So I think we'll have to defer questions till then.
Okay.
Otherwise we're going to lose our break. But I'm sure there'll be lots of questions, and I'd like to see another talk on the examples. But again, thank you very much.